Okay, let's look at this first homework question. Find the area under the curve of f of x is equal to 5x minus 2 on the closed interval from 1 to 4. Remember that this is going to be a and b. Okay, so what's happening is the following. Under this function, I'm going to create a number of rectangles, and I can calculate the area of each rectangle by multiplying the width of the rectangle by the height of the rectangle. So width times height will give me the area of one rectangle. What I want though is I want infinite number of rectangles, and I'm going to sum up the area of each rectangle to give me the area under the curve from 1 to 4. So in order to do this, we're going to do this in a systematic approach, and we're always going to find the width of our rectangle first. Width is represented by delta x. So the formula for delta x is b minus a over n. So b is 4 minus 1 over n. Delta x, or the width of each rectangle, is going to be 3 divided by the number of rectangles. So just think about this for a second. If I give you 3 rectangles, 3 divided by 3 would give me a width of 1 unit per rectangle. What we're going to do though is we're going to try to have infinite rectangles. So the number of rectangles would be infinity. 3 divided by a really big number is going to give us a width that will approach 0. The more rectangles we can get, the more accurate our representation of area will be. So width is the first thing we always want to calculate. The second thing we want to calculate for these questions is the height of the rectangle. The height of the rectangle is represented by f of x sub I. So in order to do that, we first need to calculate what x sub I is. And x sub I is given by the formula a plus I times delta x. So x sub I, a in this example is 1 plus I, delta x, the width of my rectangle, was 3 over n. X sub I is 1 plus 3i over n. So remember, we want to find the height at this point. So that would be f of x sub I, which would be f of 1 plus 3i over n. And then we're going to input x sub I into our equation, or our function, and our function was 5x minus 2. So I'm going to input x sub I in for x. So I'm going to have 5 times x sub I minus 2. Let's distribute this 5 inside. And we're going to get 5 plus 15i over n minus 2. And then I'll get 3 plus 15i over n. Okay, so now in order to find the area from 1 to 4 using limits, we're going to go on to our third step, which is find the limit. Now, the area is going to be equal to the limit as n approaches infinity. And what we're going to do is we're going to sum up the area of each rectangle. The area of each rectangle is represented by the width of the rectangle times the height of the rectangle. This will give me the area of one of my rectangles, and I want to sum up infinite rectangles on that closed interval from 1 to 4. So area is equal to the limit as n approaches infinity. Delta x, so the width of my rectangle is represented by 3 over n, multiplied by the height of one of my rectangles, and the height of one of my rectangles is 3 plus 15i over n. From here, I'm going to just distribute this inside. And I'll get the limit as n approaches infinity. and we're going to sum up the area of each rectangle. So I'll have 9n plus 45I over n squared. Okay, let's use our properties of limits to separate this into two different sums. So I'm going to get the area is equal to the limit as n approaches infinity. And I'm going to have this sum of 9 over n plus the sum of 45I over n squared. Once you set it up and you get to this step, here's sort of what your goal is. Your goal is you want to isolate i's, I squareds, or I cubes. So in this summation, I have an I that I could isolate. So I'm just going to highlight that. The reason is if I could get this I by itself, then I could use my formula for the sum of consecutive integers. So I want to get this I by itself. I need to get rid of this 45 over n squared. And what I'm going to do is I'm going to bring this to the front because this is just a number, it's a constant. So I could bring that to the front. Now over here, we don't have an I squared, or an I cubed. So if that's the case, you're going to have a constant over here. And I do have a constant. I've got the constant 9. So I want to isolate this because I know what the sum of a constant is. So in order to isolate that 9, I need to bring this 1 over n in front of the summation. Okay, this will give me the area is equal to the limit as n approaches infinity of 1 over n and then I'm going to sum 9 plus, bring that 45 over n squared to the front, and then I'm going to sum, and I've got I here, I'm going to replace that with what the formula for I is. And I'm going to replace this with the sum of a constant formula. Okay, so this is equal to the area, is equal to the limit as n approaches infinity of 1 over n. Now, 9, I'm going to replace with the sum of a constant. So the formula is using sigma notation for sum of a constant. Remember that's C times n. Now, my constant is 9, so C is equal to 9. Plus, I've got 45 over n squared. And I'm going to replace I with my formula for sum of consecutive integers. And that formula is n times n plus 1 all over 2. Okay, so what can be cleaned up here is over here, I have n over n will cancel, and I'm just going to have 9 over here. So the limit as n approaches infinity of 9 is just going to be 9. Now over here, n and n will cancel, and let's distribute this 45 inside. So I'll have the area is equal to the limit as n approaches infinity of 9 plus 45n plus 45 all over 2n. Now what I'm going to do to this part is I'm going to divide each term by the highest variable in my denominator, which is n. So that's going to give me the limit as n approaches infinity of 9 plus 45n over n plus 45 over n all over 2n over n. That will give me 45 plus 45 over n over 2. Now, as n approaches infinity, 45 over infinity is going to approach 0. So what that will leave me width is 9 plus 45 over 2. I could add these two by getting common denominators. So 18 over 2 plus 45 over 2, and that will give me 63 over 2. Square units would be the area under the curve on that closed interval from 1 to 4. Okay, let's look at one more problem. Find the area under the curve of this function on this interval using the definition of limits. So what we have is we have a quadratic. The quadratic has a y-intercept of 1. So let's just kind of illustrate this and see what's happening. They want the area from 0 to 2. So from A to B. So what we're essentially finding is we want to calculate using limits this area here. I could do that by creating rectangles. Okay? So the first thing we want to do is we want to find out what the width of one of my rectangles is. And width is represented by delta x. So the formula for delta x, in order to figure out your width of each rectangle, it's going to be b minus a divided by the number of rectangles. So 2 minus 0 divided by the number of rectangles. So 2 divided by the number of rectangles. So think about this for a second. If I have 2 rectangles, if n is 2, the width is going to be 1, right? So here's 2 rectangles. The width of each rectangle would be 1. If I have 4 rectangles, if n is 4, then 2 divided by 4 is 0.5. The width of each rectangle would be 0.5. What we want, though, is we want infinite rectangles. 2 divided by infinity would give me a width that approaches 0. The more rectangles we have, the more accurate our area is going to be. So there's the width of my rectangle, so 2 over n. Now we want to find the height of each rectangle. So if this is x sub I, the height of the rectangle is represented by f of x sub I. So second thing is we're going to calculate the height. So area is width times height. Now before we calculate f of x sub I, we actually need to figure out what x sub I is. And x sub I is given by the formula a plus I delta x. So x sub I is a is 0, plus I times delta x, and delta x was 2 over n. So x sub I is 2I over n. Now we want the function at x sub I, which is going to be the function at 2I over n. So into my function, I'm going to input 2I over n, and my function is x squared plus 1. F of x sub I is equal to, it's going to be 4I squared over n squared plus 1. Okay, so now that I've got the width and the height of each rectangle, I'm going to figure out the area of one rectangle, and then I'm going to sum up infinite rectangles. So that will take me to step 3, which is to find the limit. So the area on the given interval, it's going to be the limit as n approaches infinity. And we're going to figure out what the area of one rectangle is. So it's going to be delta x. Now delta x was, what was our width? 2 over n. So the area of one rectangle is the width. So delta x times the height of the rectangle, and the height of the rectangle is f of x sub I. Okay, this will give me the area when I multiply width times height, one rectangle. And then we're going to sum up infinite rectangles in order to calculate the area from 0 to 2. Okay, so that will give us 8i squared over n cubed plus 2 over n. Use your properties of limits to separate these into two separate sums. And then from here, our goal is to isolate I squareds, I cubes, or constants. So in this first summation, I have an I squared. I want to isolate this because then I could replace that with the formula, and this would be the formula for the sum of squares. So in order to isolate that, I need to bring this to the front. Over here, I don't have an I squared, or I cubed, but I have a constant, and I know what the sum of a constant is. So in order to isolate that, I need to bring this 1 over n to the front of my summation. So that's going to give me the area is equal to the limit as n approaches infinity of, we'll have 8 over n squared multiplied by the sum of I squared plus 2. Okay, from here, we want to replace I with our replace I squared with our formula for the sum of squares, and replace this with our formula for sum of a constant. Okay, so the formula for I squared, now I just want to see, I have somewhere that it should be n cubed. Yes. So the mistake that I made was this times this should give me n cubed here. So let me just change that. So this should be n cubed. This is n cubed. That's n cubed, and this is n cubed. Okay, so the formula for I squared, sum of squares, is going to be n times n plus 1 times 2n plus 1 over 6 plus, I have 1 over n, and the formula for sum of a constant, it's Cn, so the constant times n. Now my constant is 2, so I'm going to put a 2 here. N over n will cancel, and then I want to clean up over here. So over here, what will I have? I've got 1 n in my numerator and 3 in my denominator. So let's cancel this, and we'll have n squared now in my denominator. I'm going to divide 6 by 2 and 8 by 2. Over here, I'm actually going to combine these two binomials to give me 2n squared plus n plus 2n, so plus 3n plus 1. And then I'm going to distribute the 4 in here. So that will give me the area is equal to the limit as n approaches infinity of 8n squared plus 12n plus 4 all over 3n squared plus 2. So the limit as n approaches infinity of 2 is just going to be 2. So I need to figure out what's going to happen over here. And I'm going to divide each term by the n squared, so the highest exponent in the denominator. So I'll have 8n squared over n squared plus 12n over n squared plus 4 over n squared over 3n squared over n squared plus 2. And that's going to give me 8 plus 12 over n plus 4 over n squared all over 3 plus 2. Now, as n approaches infinity, 12 divided by infinity will approach 0. 4 divided by infinity will approach 0. So what my limit is approaching is going to be 8 over 3 plus 2. And then we'll get common denominators. And we'll have 8 plus 6. We're going to get 14 over 3 units squared. So the area under the curve on the closed interval 0 to 2 is going to be 14 over 3 units squared.